So this is the example that, yeah, I already introduced you, like housing prices. Okay. So what could be so on the y-axis, okay, this is your what is called the dependent variable, the price. That's what you want to predict. And on the x-axis, you have number of rooms, which is given to you, right? So, like how would you predict the price given the number of rooms? So you have seen some these examples, right? So number of rooms of this house is one, and the price is, let's say, something between 180. Number of rooms is two, the price is 190. Number of rooms is three, the price is 200, and so on. You're given these data, right? Now you want to predict, like, what should be the now, let's say you have trained your model and you are given another example. Let's say the number of rooms in the house is four. So, what should be the price, right? So, you can fit a straight line through these, you know, through this, through the given training set. And when you get this line, from this line, you can predict what is the price of four rooms. So, here it's somewhat around 300, right? Okay. So anything like if you are given a house with eight rooms, what is the price? You can from this line, right? Now, uh, how we are doing this. So that is the question, right? So like, you can say like, okay, so from looking at this, I mean, this can be done by naked eye, right? We can fit this line, and why do we need a machine? Right? That's the question. So can anybody tell like why do we need a machine to do this? We can do it manually, right? Right, right, exactly. So in this example, we only have number of rooms, but the price of a house might depend on the size of the house, the square feet of that house, you know, as I said, the location of the house and so on, and thousands of you know, parameters it might depend on. And you cannot, visualize, the human brain cannot visualize, beyond uh, 2D. Well, some people might visualize 3D, but mostly we cannot plot a graph beyond 2D. So anyway, but again, like we have to understand, like how is the machine doing it even for 1D, and then we can generalize it. Like we can see how the machine is doing it for n dimensions. Or yeah. So yeah. So uh, as you can see from this flowchart. So first, you have to select a machine learning model. So here the model is linear regression, right? Then you set the hyperparameters ranges for grid search. So what do we mean by hyperparameters? So this is a straight line, right? So if you can see, like this is the intercept of the line, 100. This is the slope of the line, 50, right? So these are the parameters. So you don't know these parameters from at the start, right? These are what you calculate, the 150. So you from the start, like uh, you want to fit a line, not a you know uh, curve or something. So let's say that you want to fit a line. This is a one dimensional you know linear plot, but it might not be. So I will come to that. If what if I consider like let's say another parameter, let's say number of rooms square, the square of the number of rooms. So what will happen then? So and then you do cross validation. I think the professor again has covered cross validation, and then you tune the hyperparameters and then finally evaluate your results, right? So yeah, I mean, what this exactly mean? I'll just explain in my notepad. So let me just come to my notepad. Okay, so on this axis you have given price. On this axis you have given number of rooms, right? So these are the examples that you have been given. So let's say you are fitting this line. Okay. This is the line you want to fit. Now, you want to ask yourself, like, what is the error if I fit this line? So the error you calculate as summation of all the examples that you have. Okay. Minute. Yeah. Y hat minus yi whole square. So y hat is the predicted, sorry, predicted value of price. Yi is the given or observed value of price. So these black dots are what you observe, right? So this is the value what you observe. This value, let's say 200. This is 100. So this is the observed value, right? And then let's say 300, 400. And what is the predicted value that your model is capturing here? So these are the predicted value. So for this is the predicted value, this thing. For this is the predicted value, this thing, this is the predicted value, and so on. So now, what we're doing here is calculating the difference between the observed and the predicted value. So you're basically calculating this distance, you know, this distance, squaring it, and adding it to the square of this distance, adding it to the square of this distance, adding it to the square of this distance. Okay. So that's why the summation is there at the beginning. So you are squaring the, well, this is called the least square distance. Okay. That's the name that you have. And this is the least square error basically. Okay. So if you see, these lines are, very long, but if you can fit a line like this, the mean square distance is automatically, minimized, right? So that's why you would choose this line and not the other one, right? Again, what is the y hat here? So if you like write it algebraically, y hat here is basically a plus bx, where x is the basically the number of rooms you have. And then you have to predict what is A and what is B, right? And how do you do that? You do that by minimizing this error. And how do you minimize this error? You minimize this error by doing gradient descent. So, yeah, someone has raised a hand. Can you ask? Yeah, you can ask question if you want. Donna. Yeah, yeah, right. Yeah, if you say, I mean, if you mean by hat, you mean the predicted parameters? Yeah, that's it. Right. So, gradient descent algorithm is, I think, is not covered in week one. It will probably be covered in week two. So, I'll not go into it right now. Maybe in the next week, I'll go into it when the professor has already covered it. But if you have any questions in that, you can ask me. But if not, I can move on. Is everybody able to see what I'm presenting, right? In the notepad, I can make it bigger too. Right. Now, yeah, now what if, you have number of rooms What if you have like another variable? Let's say, you know, number of, let's say the size of the house, right? Okay, it's visible, I guess. Okay, yeah. So on this axis, you have number of rooms. On this axis, you have the size of the house, and you're trying to predict the price. So this is a 3D graph. Uh, it's hard to visualize, but anyway, I'll try. So if you have, let's say you have size for a particular size for a particular number of rooms, you have the price here, and for another set of pairs, you have here, and so on. So you're populating points in a 3D space, right? It's very difficult to visualize. So this is what I'm talking about when I said about dimensionality reduction. Right? But even if you don't visualize it, we can just do it algebraically. Let's say, so what is basically we have to do here? Your y predicted will become a plus bx, let's say x1 and c x2, right? So x1 is your number of rooms, x2 is your number of, sorry, size of the house. Okay. I don't quite- Let me just fix the size here. Everybody can see the notepad, right? I mean, the letters are not too small, right? Okay, that's it's visible, right? Okay, someone has asked what is gradient descent? Explain in brief. Yeah, I will do that. I will do that. So, now your y predicted has changed, right? So, what you do is, your error will now be summation of over all the examples a hat plus b hat x1 plus c hat x2 minus the y observed yi whole square, right? And you want to minimize this error, right? So gradient descent is basically nothing but a process to minimize an error and determining what is the A, what is B, and what is C when your error is minimal, right? So the best fit line, uh, what is basically the best fit line, right? So, I mean, i- if you are familiar with calculus, you must know that, what do we do if we have to like find the minimum of a function? So this error, this is a function, right? This is some j of, you know, function of a, b, and c, right? This is the error function j. So can anyone tell me like how do you minimize a function? Right, 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 exactly. So what we'll do is that, yeah, we'll do differentiation of this function. Right. So we'll do dj with respect to a, right? And we'll see, we'll equate to 0, and we'll see what is the value of a we are getting. Similarly, we'll do dj with respect to b equals to 0, and we'll see what is the value of b we are getting, right? And so on. And we'll do it for uh, any number of parameters that we have. right? So that is the basically the method, and then we will iterate over, you know, A, B, and C until we get the best fit line, right? So that is basically gradient